Hello, in this video we'll be working through Unit 6 homework problems 35 through 38. Number 35 gives us the graph of f prime of x. So this is the graph of f prime of x, the derivative of f of x. And we're given the graph on the interval from -2 to 6. We're asked to write and find the value of a definite integral to find each of the indicated values of f below. We're also told that f of -2 equals 5. F of -2 equals 5. We want to find, in part A, the value of f of 0. So we know f of -2. We want f of 0. We're going to use those input values to set up a definite integral. So we're going to go from -2 to 0. Because we know the value of f of -2, we want the value of f of 0. So according to the FTC, the Fundamental Theorem of Calculus, we know that if we integrate f prime of x dx on the interval from -2 to 0, that's going to equal f of 0 minus f of -2. And we know f of -2. We're looking for f of 0. And on the left-hand side, we can find the value of this integral because integrating f prime is equivalent to finding the area under the curve of f prime. So we just need to find the area under the graph of f prime, which we have, on the interval from -2 to 0. So this area right here, from -2 to 0. Well, that's half of a 2x4 rectangle. So the area of the rectangle would be 8, and half of that would be 4. So on the left, that integral is equal to 4. On the right, f of 0 is unknown, minus f of -2, I do know, it's 5. And now I can add 5 to both sides of the equation, and I get f of 0 equals 9. For part B, we want to find f of 6. We know f of -2, so again, we set up a definite integral that goes from -2 to 6. We're using the input values for the function value that I know and the one that I'm trying to find. And if I want to find f of 6, I'm going to integrate f prime of x, because that's going to give me f of 6 minus f of -2. On the left, that integral is the area under f prime on the interval from -2 to 6. So from -2 to 6. Now we have some positive area, some negative area, so we'll keep that in mind. But from -2 to 0, we already saw that area was 4. From 0 to 2, that area is also 4. So we have 4 plus 4 minus, because at 2, from 2 to 6, that area is below the x-axis, so that's going to be negative area. And we have a semicircle here. The radius of the circle is 2. And so the area of the entire circle, if I drew the entire circle, would be pi times 2 squared, or 4 pi. We only have half the circle, so that area is 2 pi, and it's -2 pi because it's below the x-axis. So 8 minus 2 pi equals f of 6 minus f of -2, which we know is 5. Now I'm going to add 5 to both sides of the equation, and I get 13 minus 2 pi equals f of 6. The graph below represents the velocity, v of t, so this is a velocity graph, in meters per second of a particle moving along the x-axis on the time interval t is between 0 and 10. The initial position of the particle at time t equals 0 is 12. The position of the particle at time 0 is 12. That tells me that p of 0 equals 12. Part A, on what intervals of time is the particle moving to the left and to the right? Well, the particle is moving left when velocity is negative. It's moving right when velocity is positive, and we're looking at the velocity graph. So where is it negative? Where is it positive? Well, it changes sign at this point right here. which I could estimate to be about, I don't know, 8.25 maybe. If I want to do better than just an estimate, I would have to figure out the equation of that line, which we can do. We have some distinct points here. I know there's a point at 7, 4, and there's another point down here at 10, -5. And so we can calculate the slope, -5 minus 4 over 10 minus 7. So that's -9/3 or -3. Okay, I feel silly now. I didn't really need to do that. I could have just looked and saw that it went down 3 and over 1. So the slope is -3, and then we can write our equation, y minus 4 equals -3 times x minus 7. And I'm trying to figure out where this equation right here, this linear equation, is equal to 0. So I can add 4 over to the other side. I get y equals, let me go ahead and distribute this as well. So I get -3x, and then plus 21 plus 4 is plus 25. Where does this equal 0? -3x plus 25. So that's going to equal 0 when x is 25 thirds. 25 thirds. Or 8.3, repeating. So we can say the particle is moving right on the interval from our 25 thirds, and the velocity is 0 at 25 thirds, so I'm not going to include that endpoint, 25 thirds, all the way until 10, and that's another end point there. However, the velocity is negative at 10, and I just realized velocity negative means we're moving to the left, so let me change that. Moving left on the interval from 25 thirds to 10. Since v of t is negative. And our particle is moving right on the interval from 0 up until we reach that 25 thirds. So we already said at 25 thirds the velocity is 0, so we're not going to include that. At 0, the velocity is +2, so I will include that. So particle is moving right on the interval from 0 to 25 thirds since v of t is greater than 0. Part B, what is the total distance that the particle has traveled on the time interval from 0 to 7? Okay, from 0 to 7, so we're going to stop right here at 7. We're not going to go past that point. Total distance traveled on the time interval from 0 to 7. Leave your answer in terms of pi, indicate units of measure. On the interval from 0 to 7, the velocity is positive the entire time. It's positive, which means the particle is moving right the entire time. It never changes direction, and therefore the total distance traveled is going to be the same as the net distance traveled. Net distance is a much simpler calculation, so you want to be sure before you just use that net distance calculation that your total distance truly will equal your net distance. In this case, it will. So the total distance from 0 to 7 is just going to be the change in position from 0 to 7. So p of 7 minus p of 0. Now, this is not the graph of p, so I can't just look at 7 and see what the y-coordinate is. This is the graph of v of t. So to get p of 7 minus p of 0, I want to think about what is the derivative of position. Well, it's velocity. So if I integrate velocity, I'm going to get position. And if I integrate it from 0 to 7, I'm going to get position at 7 minus position at 0. This, again, comes from the fundamental theorem of calculus. The value that we have right here is the antiderivative of the function that we're integrating, and the antiderivative of velocity is position. So we evaluate position at the upper bound 7 minus, and then evaluate at the lower bound 0. We know that P of 0 is 12. That was given to us in the problem. So P of 0 is 12. We're good there. P of 7 we don't know. And the integral from 0 to 7 of the velocity would just be the area under the curve, and that we can figure out because we have known geometric shapes forming that region. So from 0 to 3, we're going to split this up into parts. From 0 to 3, you can either make this a rectangle and a triangle, or you can use the formula for trapezoid to get the area. I think the rectangle and triangle will probably be faster. So this is a 3 by 2 rectangle. It has an area of 6. The triangle above is just half of a 3 by 2, so it has an area of 3. And then from 3 to 7, it's this big rectangle, actually square. It's a 4 by 4 square minus this semicircle. So the 4 by 4 square is 16, but then I need to subtract the area right here of this semicircle, and this is a part of a circle with radius 2, so 4 pi would be the area of the whole circle. 2 pi would be the area of the semicircle, so I need to subtract 2 pi. Now if I add those three regions together, I get 9 plus 16, so 25 minus 2 pi, and that's the integral of velocity from 0 to 7. That's equal to P of 7 minus P of 0, which I know is 12. And now that I think about it, I mean, I'm sort of in the process of solving for P of 7. I don't need to solve for P of 7. It's asking me what's the total distance, and we already said we really just need the net distance, so we need P of 7 minus P of 0. And that's already what we have on the right, is P of 7 minus P of 0. So really our final answer is just what we have here on the left, 25 minus 2 pi. Part C, what is the net distance that the particle travels on the interval from 5 to 10? So we're going to start here at 5, and we're going to stop here at 10. We want to set up an integral then. This is v of t. So we can set up our integral from 5 to 10 of v of t dt, and that's going to be p of 10 minus p of 5. And p of 10 minus p of 5 is the net distance traveled from time 5 to time 10. So we just need to find the area under this velocity curve from 5 to 10. And again, we'll break this up into known shapes. So let's go from 5 to 7, and then from 7 to this value, which we already figured out earlier was 25 thirds, and then from 25 thirds to 10. From 5 to 7, we have a rectangle minus a quarter of a circle. The rectangle is 2 by 4, so the whole rectangle is 8, and we have to subtract that quarter circle. And we already said before, since radius is 2, the whole circle would have an area of 4 pi, half the circle 2 pi, and a quarter of the circle pi. So 8 minus pi is going to be this area that we are interested in here. And then for our triangle, unfortunately, this side length isn't an integer value, but we're going from 7 to 25 thirds. Okay, so that length right there is 25 thirds minus 7, which is 21 thirds. 21 thirds, and that will give me 4 thirds. So that side of the triangle is 4 thirds. the height of the triangle, 1, 2, 3, 4, is 4. So the area of my triangle, area of that triangle from 7 to 25 thirds, would be 1/2 the base times the height, or 16 over 6, which is 8 over 3, 8 thirds. So far we have 8 minus pi plus 8 thirds. Now the area down here, we've got a triangle that goes from 25 thirds to 10. So that area of that bigger triangle, we've got 1/2 times 10 minus 25 thirds times the height here is 1, 2, 3, 4, 5. So 10 is 30 thirds. 30 minus 25 over 3 is 5 over 3. So we have 5 over 3 times another 5 and then over 2, which is 25 over 6. And that area is negative. So minus 25 over 6. Okay, and 8 thirds is 16 over 6. So we have 16 minus 25, I believe that's negative 9. So 8 minus pi minus 9 over 6. 9 over 6, if we divide top and bottom by 3, we get 3 over 2. 8 minus 3 over 2 is 16 minus 3 all over 2. So 13 over 2, and then minus the pi. Okay, so it said to, oh, this one doesn't say to leave pi in our answer. This one says round your answer to the nearest thousandth and then indicate units of measure. Well, if we are integrating, the velocity has units of meters per second. So when we integrate that, we just get back to plain old meters. Meters minus meters. So this will be in meters. And if we round that to the nearest thousandth, let me grab the calculator. We've got 13 over 2 minus pi. 3.358. 3.358 meters. Part D, what is the acceleration of the particle at time t equals 2? Acceleration is derivative of velocity. So we are asked here to find v prime at 2. And since we have the graph of v of t, the derivative of v will just be the slope of the graph at 2. And thankfully, that slope is occurring on a linear portion of the graph. So I can just use rise over run to figure out the slope. So I'm going up 2 and over 3. So 2/3. And then if the units on velocity are meters per second, the acceleration is meters per second squared. And part E, what is the position of the particle at time t equals 5? So we need to find P of 5. We know P of 0. So we can set up an integral that goes from 0 to 5, and if we integrate velocity, we end up with position. So the integral of v, nope, I didn't need that prime there because velocity already is the derivative. We want to integrate velocity, and that gives us position. So that's going to equal P of 5 minus P of 0. The integral of the velocity from 0 to 5 is just going to be the area under the velocity curve from 0 to 5. And this one, what did we say this was? 6 and 3. And here, we found this before. We went from 3 to 7, so I just need half of what that was before, but I can't remember what that was before. So just start over again. So we've got this 2 by 4 rectangle, which is 8, minus a quarter of the circle. The whole circle was 4 pi, so a quarter of the circle was pi. So here, 8 minus pi. So we have 6 plus 3 is 9, plus 8 is 17. So 17 minus pi equals p of 5 minus p of 0. We know p of 0 is 12. So now if I add the 12 over to the other side, I get 29 minus pi equals p of 5. And p of 5 is the position of the particle at 5, so the units there would be meters. P of 5 equals 29 minus pi meters. (37) Pictured below is the graph of a function that represents a particle's velocity on the interval from 0 to 4. So this is the graph of v of t. For what values is the particle moving to the right? For what values is it moving to the left? So the velocity curve, let's think about where it's positive, where it's negative. It's positive from 0 to 1, not at 1. It's positive from 1 to 2. It's positive from 2 to 3, but not at 3. So wherever the velocity is positive, our particle is moving to the right. So we can say the particle is moving right on the interval from 0 to 1, so not at 1, but it is positive at 0, so we'll include that, union, and then from 1 to 3, not at 3, and that's it. The particle is moving right on the interval from 0 to 1, union 1 to 3, since v of t is greater than 0. And then the particle is moving left on the interval from 3 to 4. At 3, the velocity is 0, so it's not moving left at 3. At 4, the velocity is negative, so we will include the 4. So since v of t is less than 0. C and D, for what values is the speed of the particle increasing and decreasing? So now we want to think about where is the velocity, positive, negative, where is it increasing, where is it decreasing? So it starts out positive and decreasing. If the velocity is positive and decreasing, if the velocity is decreasing, then its derivative is negative, so acceleration is negative. So they have opposite signs. So the speed, well, I think we're going to have different reasons. Since we have to justify, I can't combine this like all into one. So let's just start out. We'll just go from left to right. So on the interval 0 to 1, the velocity is positive. That's why I didn't include the 1, because it's not positive at 1. The velocity is positive and decreasing. Therefore, speed, it's slowing down. So speed is decreasing. Then, on the interval from 1 to 2. So here I want to say the velocity is positive, and it's not positive at 1, so I'm not going to include the 1. But it is positive at 2, so I'll include the 2. On the interval from 1 to 2, the velocity is positive and increasing. Therefore, speed is increasing, speeding up. Okay, then we have the interval from 2 to 3. On the interval from 2 to 3, and here I want to say the velocity is positive and decreasing. So at 2 it is positive, at 3 it is not. So on the interval 2 to 3, the velocity is positive and decreasing. Therefore, speed is decreasing. And then finally, we have the interval from 3 to 4. So here I want to say the velocity is negative, and at 3 it is not negative, but at 4 it is. So we don't include the 3, but we do include the 4. So on the interval from 3 to 4, velocity is negative. And decreasing. So negative and decreasing means velocity and acceleration are both negative, so the speed is increasing. It's speeding up. Therefore, speed is increasing. Now, another way to answer this question or to justify it would be to create a speed graph. And the speed graph is just the absolute velocity of the absolute value of the velocity graph. So if we took the absolute value of this graph, wherever it's positive, that just is going to stay the same. And where it's 0, it's going to stay the same. So all it's going to look the same on the speed graph. All this stuff is going to look the same. But then when the velocity is negative, we have to reflect that across the x-axis. So the speed graph here is going to go up at the end. So now we can see the speed is decreasing from 0 to 1, increasing from 1 to 2, it's decreasing from 2 to 3, and it's increasing from 3 to 4. So that would be another way that we could justify our answer there. And part E and F, what is the net and total distance that the particle travels on the interval from 0 to 4? Well, the particle does change direction at 3. We can see that on the graph because the velocity changes from positive to negative. So we're going to have to split this interval into 2 subintervals. We'll find the distance traveled from 0 to 3 and then from 3 to 4. Now, if we just want net distance, like part E, we don't have to split it. We can do that with a single calculation. So for net distance, we would want P of 4 minus P of 0. But this is not the position graph. This is the velocity graph. So we can't just read those values from looking at the graph. We have to integrate the velocity in order to determine the change in position. So I would want to set up an integral where I'm integrating velocity from 0 to 4, and that's going to give me my net distance traveled. So that's going to be P of 4 minus P of 0. Now the integral of velocity from 0 to 4 is the area under the curve from 0 to 4. So we will find the area from 0 to 2 first. The area from 0 to 2 is going to be this 2 by 1 rectangle, which has an area of 2, minus the semicircle. So the semicircle here has a radius of 1. That means the area of the whole circle is pi. We have half the circle, so pi over 2. We're subtracting pi over 2. Then I'm finding the area from 2 to 3. Well, that's half of a 1 by 1 rectangle, so 1/2. And then I keep going from 3 to 4. That's going to have an area of negative 1/2. So the 1/2 minus 1/2 is 0, and 2 minus pi over 2 is equal to P of 4 minus P of 0, which is my net distance. So 2 minus pi over 2 will be my net distance. Now total distance, we're going to find the area from 0 to 3. That's the positive area. So that was the 2 minus pi over 2 plus 1/2, that. And we're going to add the absolute value of the area from 3 to 4. So another 1/2. So this is going to give us a different answer. So now we've got the 1/2 plus 1/2 is 1, plus the 2 is 3, minus pi over 2. So the total distance traveled is 3 minus pi over 2. Number 38, a car travels on a straight track. During the time interval, t goes from 0 to 60 seconds, the car's velocity v measured in feet per second and acceleration a measured in feet per second are continuous functions. The table below shows selected values of these functions. Using appropriate units, explain the meaning of the integral of the absolute value of v of t dt on the interval from 0 to 60 in terms of the car's motion. And then we're going to approximate this integral using a midpoint Riemann sum with 3 subintervals. If the absolute value were not there, if it was just the integral of v of t dt from 0 to 60, that would give us p of 60 minus p of 0, which is the net distance traveled. When you take the absolute value of your velocity, then you just get positive area the whole time. So it's going to give you the total distance traveled. So this integral from 0 to 60 of the absolute value v of t dt gives the total distance the car travels from t equals 0 to t equals 60 seconds. Approximate this using a midpoint Riemann sum with 3 subintervals. So we use the midpoint Riemann sum on the velocity equation. Okay, we've got several rows in our table here, but I'm looking at the velocity row. I'm doing a midpoint Riemann sum with velocity to try and approximate the area under the velocity curve. 3 subintervals from 0 to 60. So I'm going from 0 to 25, and then 25 to 35, and then 35 to 60. The width of the interval here is 25, here is 10, and here is 15. Wait, did I do that right? 35, 45, 50. No, that's 25. And then the midpoint Riemann sum means I'm using the midpoint y-coordinate for the height of the rectangle. So I have 25 times negative 30 plus 10 times negative 14 plus 25 times 0. Now this would give me the net distance. This Riemann sum is going to give me the net accumulated area. And that's not what I want. I want the total distance traveled, so I really need to take the absolute value of the velocities. So I want to multiply by the absolute value of negative 30 and the absolute value of negative 14. So 25 times 30 plus 10 times 14 plus 25 times 0. That one's just going to be 0. So this would give me net distance, an approximation for net distance. This one is going to give me the approximation for total distance. And 25 times 30 plus 10 times 14 is 890, and the distance is measured in feet. Part B, using appropriate units, explain the meaning of the integral of a of t dt from 15 to 50 in terms of the car's motion, and then find the exact value of the integral. If we expand this or evaluate this using the fundamental theorem of calculus, we see that this is going to equal the antiderivative of acceleration is velocity, so the velocity at 50 minus the velocity at 15. So it's giving us the change in velocity over this time interval. So this represents the change in velocity, and it's the net change, maybe I should say that, the net change in velocity from t equals 15 to t equals 50 seconds. We can find this exact value because we have v of 50 in our table. V of 50 is 0, minus v of 15 is negative 30. So that's equal to 30. This is the change in velocity, and velocity is measured in feet per second. Part C, is there a value of t such that a prime of t equals 0? If so, on what interval does such a value exist? Justify your reasoning. A prime of t equals 0 means the derivative of a is 0. So that sounds like Rolle's theorem. Rolle's theorem guarantees that somewhere on an interval, the derivative of a function will equal 0, provided that certain conditions are met. So we will need to check those conditions. Is the acceleration function continuous and differentiable on the interval we're working with? Well, we know that it's continuous because we were told that in the problem. It is continuous from 0 to 60, including at the endpoints. And we can see the endpoints are defined. So it is continuous on the closed interval. I'll go ahead and say that. Maybe first we should try and figure out what interval we're working on. So continuous on the closed interval. Is it differentiable everywhere from 0 to 60? Well, we're not told that it is differentiable, but what would it mean for it not to be differentiable? That would mean that our acceleration function would have to have a corner or a cusp or a discontinuity. And since this is a real-life scenario of a car traveling on a track, it wouldn't make sense for our acceleration curve to have a discontinuity in it, or a corner or a cusp. So I think it's reasonable to assume in this case that it is differentiable. And then the third condition we have to check is that the endpoints of our interval have the same acceleration values. So we're going to look in the table and we're going to find, if we can, two time values that have the same acceleration. And we've got a couple of options here. The acceleration is the same at 0 and 30. The acceleration is the same at 25 and 35, and at 25 and 60, and at 35 and 60. So there are actually several intervals that contain a value c where a prime of t equals 0. It's going to happen somewhere between 0 and 30. It's guaranteed to happen somewhere between 0 and 30, somewhere between 25 and 35. I'm talking about time values here. Somewhere between 35 and 60. Okay, so let me just work on the interval from 0 to 30 first. So we can say a of t is continuous on the closed interval 0 to 30 and differentiable. Again, we're just saying that it's reasonable to assume that it is differentiable in this case, and differentiable on the interval 0 to 30, and a of 0 is equal to a of 30. Therefore, there exists a value c in the interval from 0 to 30 such that a prime of t equals 0. Now the same can be said, so I'll say likewise, there exists a c in the interval from 25 to 35, and somewhere between 25 and 60, and somewhere between 35 and 60. 35 and 60. So you could have chosen any one of those four intervals and argued that, yes, there has to be a place where a prime of t is 0 by Rolle's theorem. And let me just write down the name of the theorem that I used. Okay. Part D, using appropriate units, approximate the value of v prime of 31. What does this value say about the motion of the car at t equals 31? So v prime is acceleration. We want to estimate the acceleration at 31. So we know the acceleration at 30 is 1. The acceleration at 35 is 2. So you might say, well, it's probably just a little bit more than 1. Mathematically, how can we estimate it? Well, we can use, so v prime is the instantaneous rate of change of v, and we can use the average rate of change of v to estimate that. So we would go to the closest surrounding points around 30, and we'd find the slope of v. So -10 minus -20 over 35 minus 25, which would give us 10 over 10, or 1. And if we had just said, well, it's a little bit more than 1, we can see that we're getting about the same answer there. Our units here, feet per second squared, since we are estimating acceleration. What does this say about the motion of the car at t equals 31? Since the acceleration is positive, well, you could say you have positive acceleration, that means our velocity is increasing. So the velocity at this time is increasing. Now, the velocity at this time is negative, presumably, because at 30 it's -14, at 35 it's -10. It's negative, but it's increasing because the acceleration is positive. We can also see it's increasing because it's going from -14 to -10. So the car is slowing down at this time. So it seems a little counterintuitive to say the velocity is increasing and yet the car is slowing down. But it's because the velocity is negative and increasing. So it's getting closer to 0. The velocity is getting closer to 0, so it's slowing down. And part E, using appropriate units, find the value and explain the meaning of 1 over 35 times the integral of a of t dt from 25 to 60. And note that the difference between 25 and 60 is 35. If we do 60 minus 25, we get 35. So this is the average value formula. The average value formula is 1 over b minus a times the integral from a to b of f of x dx. So here we have the average value of whatever function you have here, which is, in our case, is a of t. So we're going to be finding the average. This is going to give us the average. If we put an a of t right here instead, then I got to make that. Okay, that's getting really messy. A of t dt, that gives us the average value of the acceleration, which is a more awkward way of just saying average acceleration, on the time interval from A to B. And we know when we integrate acceleration, we get velocity. So this is going to be 1 over b minus a v of b minus v of a. And in our case, let's go ahead and put in our a's and b's. So 1 over b minus a is 1 over 35. V of b would be v of 60, and v of 60 is 10. V of a is our v of 25, and v of 25 is negative 20. So we get 30 over 35. This is the average acceleration, so the units are feet per second squared, is the average acceleration from t equals 25 to t equals 60 seconds.